All right, guys, we're going to do a quick introduction to fluids. Let me get it started here. So here, these are the equations. We're going to do this over, we're going to break this into parts. We're going to do the fluids at rest. And then you can see the four equations there. We'll talk about them. And then fluids in motion, we will separate out, but we will do that. So again, a lot of the demos are tricky to record, but here's one. You can actually download an app on your phone that'll measure pressure, and then just let it sit there on a desk or something and see what the pressure is. Then put it in a Ziploc bag, fill the bag with air. You can pause it on the screen and read this, but and see if there's a change in pressure. And what you'll see is that there's not a change in pressure. And then now you're going to squeeze the bag. Then you actually increase the pressure. But it's cool to see. You can see the numbers actually fluctuate. The states of matter real quick. There's four common ones. There's some other less common ones, but these are the big ones. So solid, obviously shape, volume, that's set. Liquid takes the shape of the container, but has a definite volume to it. Gas will take the shape and volume of the container. And then plasma is just an ionized gas. I throw that one in there just so it's a heated up gas. We will focus on, since it's fluids, liquid, gas, but plasma would also follow some of these rules. What is the most common state of matter in the universe? You got solid, liquid, gas. If you're limiting yourself to Earth, then it's a different answer. But if you think all over the universe, stars is a plasma, so it's the most abundant. And then again, what is a fluid? Any substance that can flow and conform to a container. So like I said, liquid, gas, plasma. We're going to focus on these things called Newtonian fluids, which just means their flow rate is proportional to the stress, which you don't need to know that. I'm just saying it's not like my example there. It's not ketchup, honey. If you've ever played with like oobleck, like that kind of stuff is non-Newtonian. And then unlike solids, so solids, like everything we've done so far has been based on mass and force. Fluids is going to be density and pressure. Oh, and then so here, the picture here. We're looking at this kind of flow. I don't know that you can see here. Let me put on the laser pointer. This flow where it's smooth. This is turbulence and won't follow the rules that we're going to talk about. Won't follow them as well. It might follow them a little bit, but not as well. And then the first thing we're going to start with fluids is density. That's the Greek letter rho. You'll see it when I do the the problems. M is mass and V is volume. And by volume, we're going to do it in cubic meters. So you got to picture something a meter by a meter by a meter is what we're specifying as volume. So if you took a cubic meter of interstellar space, it'd be 10 to the negative 20. So it's not completely empty. Here, I'll give you some. So rubbing alcohol is 785 kilograms. Ice is 917. Water is around 1,000. You can go higher. You can see the chart here. Again, you can pause it and look at these other ones. There's a cool demo you can do. All you need is rubbing alcohol, like 90% rubbing alcohol that you would use for like cuts and stuff at cleaning. Some people use it for cleaning. But you put rubbing alcohol has a density of 785. Ice has a density of 917, and water has a density of 1,000. So if you anything, what floats is when you have less density than the object you're in. So you put an ice cube in water. Ice has a density of 917. Water has a density of 1,000. So ice floats. But if you put ice in rubbing alcohol, 90%. So it's got to be I know 70% might work. I'm not sure. I feel like they sell both, but again, just normal cleaning rubbing alcohol. You put an ice cube in it, it'll sink. I think it has to be higher up on the percentage, though. You'll have to tell me if 70% works. I know 90% works. I don't know if 70% works. The videos, unfortunately, I cannot show you because YouTube will flag me. But if you look up here, also the demo, if you take baking soda and vinegar, and it'll make carbon dioxide. Just pour it, let it fizzle up a little bit, and where that gas that's in the container is actually more dense than air, you can pour it out over a lit candle. It'll put it out. And then there are gases that are denser than air, and it makes you know how people inhale helium, and it makes their voice higher. There's gases that you can inhale that actually make your voice lower. And again, it's all density stuff. But the denser material is harder to vibrate, so your voice sounds deeper. Density and floating, just again, I've mentioned this, but if you're less dense than the material, you float. So then that is why we can't fluctuate our mass. So we got, this is the inside of a fish that it's, I forget what that's called. It's some kind of bag. It's basically, it's, they don't breathe air, right? But so they don't have lungs. We use our lungs to change our volume. So you increase the volume, you drop your density, you float. When you exhale, you sink to the bottom because you decreased your volume and increased your density. Fish do the same thing, but with this weird little bag thing, they can go up and down. Oh, the actual question. So density change. Yeah. So the mass can't stay the same. So if you want to be more dense than the liquid you're in, and you want to actually sink down into it, then you got to decrease your volume, and then that is where we exhale air out. All right, classic fluids problems we'll talk about later. What is pressure? It's represented by the variable, it's a capital P. Here's the equation down here. So pressure equals force per area. This might have been something you did in middle school, but here, I'll use the pencil real quick. If you poke yourself, push with the same force, but poke yourself with the pencil head, the writing part, and then poke yourself with the eraser part, they feel different. Even though you're pushing with the same force, they feel different. That's pressure. Bed of nail, if you've ever seen any, I don't know, videos of people on bed of nails, right? You sit on, you put your hand on one nail or you sit on one nail, that's going to go through, it's going to puncture you. But you sit on 100, it distributes your weight over 100, and then that's pressure. And then you can, if you've ever seen your tires, if you looked at them when they're like losing air, what happens to the area of a tire if the pressure is cut in half? Well, I don't think that's animated. Nah, usually I put the arrows down here. But if I cut this, if I drop the pressure, the weight of the car doesn't change. 4F doesn't change, but the area of the tire gets bigger. And then that's what's happening with the picture here. And then units, real quick, it's measured in pascals, which is short for force units, which are newtons, area units, which are square meters. So we get the newton per square meter. And then we call that the metric, we call that pascals. You've in our units, PSI, pounds per square inch, is what you've heard it as. And then that just reminded me that I did not talk about the units for density. It's kilograms per cubic meter. So mass is kilograms, volume is cubic meter. So it's kilograms per cubic meter is what we'll use for density. All right, and then so a little side thing on air pressure. Air, we consider it 1 atmosphere on average, or what is it, standard temperature, so like room temperature. We consider 1 atmosphere around 100,000 pascals, which breaks down to 2,100 pounds per square foot. So if you can picture almost like the area of your Chromebook, there's 2,000 pounds of air pushing down on that. And now if you go to the square inch, if you want to think about an inch, there's 15 pounds a square inch. And then in meteorology, they use mercury, inches of mercury, and then it has like the barometer and that kind of stuff. Pop bottle, sorry, I can't, that one's tricky to show you. Why do we need to notice air pressure? Why are we not crushed? The air pressure inside us is equal to the air pressure outside of us. Same reason why 2,000 pounds of per square foot doesn't crush your Chromebook. There's air inside it pushing back, and then those cancel out. So we're equal in and out. When do we notice air pressure is when we change altitude. We go higher up, we go lower down, or we go underwater. Like anytime there's a pressure change, our ears can tell. And then you got more pressure on the inside or outside. Vacuum seal. Sorry, we got to skip some of the demos. The Airzuka demo, it's a cool little toy, but it's just here, I would look it up, but it's a little cannon looking thing with a like stretchy band and a plastic bag, and it condenses the air really quick and creates a pressure difference. So we notice when there's pressure differences, then we notice it, and then that's how air, like wind, travels across. Pascal's principle is just an extension of the equation. Pressure equals force per area. He found out, Pascal was the first to do this. If you confine a fluid, so here I have a fluid over here on a small cylinder is attached to this larger cylinders, and then this is a hydraulic lift. If anyone's you got a fancy way to lift your car that uses fluids, it's a hydraulic. But the idea is it's a contained fluid, and when you contain a fluid, whatever pressure you exert on one side, you get the exact same pressure on the other side. So you can manipulate force and area. And then this is one of the problems we'll come across. So how does the pressure applied on the left compare to the pressure on the right? The pressures are equal, but the areas are different, which means the forces are different. And so because this side has a smaller area, well, no, we'll jump over here. Since this side has a larger area, you get more force from the output. So you put a little force over here on a small area, you get a large force over here over a bigger area because they have to equal each other. Pressures on each side have to equal each other. And then there's a problem. We'll do those later, like I said. Pressure and depth. So here, a little math thing real quick, but then you can just use the equation. Pressure equals force over area. And so if we're talking about, in this case, of water, we're going to say the weight of the water. Weight's mass times gravity, and then you got divided by area. Mass, we can go to the density equation. Density is mass per volume. Solve for mass, you get density times volume times the G from the mg divided by area. Well, volume divided by area, length times width times height divided by length times width. The lengths cancel, the widths cancel, and all you're left with is h. So the shape of the container is irrelevant. It's the depth that you're in the container that matters. So the equation breaks down to pressure equals the density of the fluid times gravity times the h is the depth. And then that's why that answers this question. Why is the area of the water above not a factor? Because when you do volume divided by area, those factors cancel out. All right. Here's just a silly one. Gauge versus absolute pressure. So gauge pressure. There are gauges, different gauges measure pressure. Some account for not air resistance. Some account for our atmospheric pressure, and some don't. If it's just the gauge, then they zeroed out the atmosphere, which is like your tire gauge. It doesn't measure the pressure of the tire and the atmosphere. It just measures the pressure of the tire. If it's what we call absolute pressure, then we add in the atmosphere, this P naught. And then P naught is just 1.01 times 10 to the 5th Pascal. Sometimes they'll use 1 times 10 to the 5th Pascal. So if our answers are ever off, it might be that I used 1 instead of 1.01. But either one is acceptable. And then the density of water is a given. It's around 1,000 kilograms per cubic meter. I think actually it's exactly 1,000 kilograms per cubic meter. I think we define density based on that. I might be making that up. But anyway, atmospheric pressure and the depth. So equation-wise, so absolute pressure is going to be P naught, the atmosphere's pressure, plus rho GH. And then if it wants gauge, all you do is get rid of the P naught. So you can write it down as separate equations, or just zero this out if you come across a gauge question. And then it should specify. Here, this is a Mythbusters video, but why snorkels can't be longer than a foot? I don't know if you've ever snorkeled, but the snorkels are only like a foot. Why can't they be longer? Is going back to this equation. You increase the pressure based on depth. So the deeper you go, the more pressure difference there is. So if you go, let's just say it's like a 3-foot snorkel, the pressure at the surface of the water is going to be more. Other way. Sorry, it's going to be less because you're 3 feet underwater. There's more pressure because of the water. It's going to be more underwater than it is above water. So if you go down holding your breath, your lungs are pushing out with an equal pressure that the water is pushing in. If you put your mouth on a 3-foot long snorkel, you just opened your lungs to a low pressure above the surface, and then the water just squeezes you. It's called lung squeeze. This animation right here, it was real. This isn't a fake video. They steamed, and you might have seen a demo like this done with pop cans, but they steamed the inside. They steam cleaned the inside of this tanker, and then they closed the lid. Well, over time, the steam condenses to water and creates a low pressure, and then the atmosphere just crushed the thing. Here's some demos real quick. The easiest one to explain. I'll do a couple. And you can pause this and try some of these, but water in a straw. If you've ever taken a straw, put your finger on top and lifted it out of the water or pop or whatever you're drinking, the liquid comes out, and then you remove your finger and it drops the liquid back into the cup or your mouth, wherever. How that works is you created a pressure difference inside the container. So for the straw, for example, when you pull the straw out, you'll have to notice there's a little, um, when you pull it out, gravity pulls a little of the liquid down. Sometimes a drop falls off, sometimes it just hangs there. Regardless, though, that the liquid dropped in level just a hair, but it was enough to create a low pressure inside the straw. And so the air from the atmosphere tries to go up inside the straw and actually holds the liquid in place. um, coffee cup lids. Um, any hot drink that you ever had has a hole in the backside. Like it has the mouthpiece where you drink out of, and then so plastic lids is what I'm talking about. It has a hole in the backside. So when your mouth's covering up and the liquid's covering up the main hole that you're drinking out of, air comes in through that back hole. If you ever close off, put your finger on top of that back hole, you'll actually have to suck the liquid out because the atmosphere won't. When you tip it, some of the liquid goes in your mouth. It creates a low pressure inside the cup, and then the atmosphere tries to get in. Well, if your mouth's stopping it, um, some of the air has to bubble through the liquid. I'm sorry, if the liquid's blocking the hole and you're blocking the other hole with your finger, air has to come in and try to get through the water. So that's when it glugs. And then that's how siphons work. You create a low pressure. We'll do some problems. We'll do a lab. Here, keep going real quick. Pressure differences. So inside a closed container, the pressure is equal throughout. When you go beneath the surface of the water, as you go deeper, the pressure increases. So the pressure above you is less than the pressure below you. And this is what we call the buoyant force, a pressure difference. So in a trapped container, you don't have a pressure change. In an open container, you do have pressure changes, and we call that the buoyant force. And again, here is, you don't have to know them how the equation came to be. We're just going to use the equation. But here, this is what's happening. You got force on top is pressure times area, and then you got force on the bottom is pressure times area, right? Which is pressure equals force over area. They just rearrange the equation. But you can, that comes out as if you change pressure, right? Pressure is height times density times gravity times area. And then, so this equation becomes H2 anyway. When you take the difference in those two forces, we call that the buoyant force. And it breaks down into this. You just need the density of the fluid, not the object. The object's density does not matter for calculating the buoyant force. It will matter if it sinks or floats, but not for calculating the buoyant force. And the buoyant force is what's, you feel it when you go underwater. You feel that water pushing up on you. That's the buoyant force. But the density of the fluid, the volume displaced by the object. So if the object's fully submerged, and this you'll do in the lab, the volume of the object, as long as it's completely submerged, equals the volume displaced. And then you multiply by 9.8, and it's positive 9.8, not negative. Again, I can't show videos because they'll flag them since I'm posting this, but Archimedes Eureka moment video, if you look it up, it's a decent little quick little summary of Archimedes' principle. But all it is this, what we just talked about. If you he figured out that when you submerge an object in water, the displacement of the volume of water is equal to the volume of the object, as long as it's fully submerged. If it's only half submerged, then it's half the volume. And so the equation, so this is the buoyant force equation, equals the density of the fluid. So if it's water, it's 1,000. Volume displaced. If the object's fully displaced, then it's the volumes are equal. If it's only half displaced, then it's half the volume times gravity. And then that also equals the mass of the fluid displaced. So if you put something in a container and collect the water that comes out, the displaced water, if you let it pour out the side and collect it, you multiply that by, collect that and measure its mass, that's also equal to the buoyant force. And then just a couple about buoyant force and floating. So here, this first part, when the buoyant force is greater than or equal to the weight of the object, it floats. So the buoyant force has to be greater than or equal to. So how can sinking an object be made to float without changing its weight? You change its volume. You make it bigger. You increase the volume. Increasing the volume increases the buoyant force. So here's an instance where the buoyant force is greater than the weight, and this thing will rise. If you've ever taken a balloon or a ball and held it underwater, you can feel it pushing up on you. Or a kickboard, if you're swimmers, you can feel that buoyant force pushing up on that thing. You let it go and it shoots to the top. That's when the buoyant force is greater than the weight. If the buoyant force is less than the weight, like this one, then it's going to sink. If the buoyant force is equal to the weight, you have two possibilities. Either you're going to float with some of the object above the water, or the whole object could be right at the water line, or just chilling in the middle. It just depends on the densities, how the density compares to water. Well, here we'll talk about that since I brought it up. If the density of the object is less than water, it'll float above the surface. If the density of the object is equal to water, it will float beneath the surface, but still float. All right, problems. We got a couple problems. Those were all. So we talked about stuff when there's a pressure difference. This is also pressure differences, but what happens when there's a lack of pressure? And then this is getting into space, right? Vacuums. It's devoid, not completely, but enough that the high pressure wants to go fill it. So here's my quick little. Sorry, I can't record these silly demos. But what would happen to a human in the vacuum of space? We are not airtight, so now we can hold our breath. We can close our lungs off, and then our lungs are airtight. But the air outside of that, trapped in our body, would just go out, and so we would swell up. Kind of like if you've ever microwaved a marshmallow, the air, that pressure change inside the molecule, we'd puff up. We don't blow up, but we'd puff up. Now, if you hold your breath, your lungs could swell to the point where they break. Again, not blow up, but they could crack, tear. I think the term is tear. But so if you happen to find yourself out in space, you'd want to exhale. As bad as that sounds, you're going to run out of air, but your lungs aren't going to tear. So if you got back inside quick enough, you'd be okay. Water in a pressure vacuum starts to boil at a lower temperature. I don't know if you've looked at cooking instructions. They cook different at higher altitudes. And then the pressure gauge, just the pressure drops, obviously. And then here, wear sunscreen. The sun's rays they're not blocked by our atmosphere. So out in space, that would be a bad thing. Glass bottle breaking. I'm going to preface this. You can look it up online, but I'm going to explain it real quick. But just be cautious. I don't think the video's it's not going to show you. You have to wear a glove that's like leather that won't cut you with glass, because you're breaking glass if you ever tried this. So I'd wear leather gloves so it doesn't happen. Or I highly recommend just watching the video. But it's breaking a glass bottle. When you fill it somewhat with water and you just hit the top, when it falls, the water stays where it is and the bottom of the bottle drops. It creates a little mini vacuum, and then the fluid tries to rush back down and fill that vacuum, and it's enough that it could break the bottle. So you got to definitely wear leather gloves, or again, safety reasons, just watch a video of it. But that's what those are all pressure demos. All right, we're going to stop there, and then those were all fluids at rest. We'll talk about fluids in motion later, like I said. Sorry guys, I don't know how to stop this video. Here we go. All right.